Hello and welcome to video lesson 14 on transverse shear stress. Our learning objectives are to be able to state and apply the transverse shear formula. For this session, you should read Beer and Johnston section 6.1. So if we're talking about transverse shear stresses, we're talking about the shearing stresses that will develop in a beam subject to a transverse load. And if I was to take a look at a small square, these shearing stresses are going to act on a square as I've drawn them for this particular case. And these can cause failures in different ways in beams. Uh, for wood, you have very weak planes in shear. And if you have an overstressed railroad tie, for instance, you might have a split that runs down the middle because the transverse shear stress is very high near the point where the railroad rail sits on the cross tie, and you could see a horizontal split in a weak plane of shear for wood, and you could see a failure that looks like that. However, for concrete, you might see shear cracking that happens at more of a 45-degree angle orientation. And you can imagine that these two shear stresses pull downward, and these two shear stresses pull upward. And you end up with concrete in tension, and concrete is extremely weak in tension. And you can have shear cracks that would come at a 45-degree angle, and without adequate ties or stirrups in a concrete beam, shear cracking could cause a concrete beam to just drop out between the supports. So calculating transverse shear stress is a very important thing for us. And what we want to do is we actually want to describe the magnitude of the stress as a function of where we are vertically on the beam. So we typically have high stress near the neutral axis. We have much lower stress near the edge of the beam, the top or bottom edge of the beam, and it's distributed uniformly laterally through the beam. Now, our book will define a topic called shear flow, and that's called lowercase q. And that's given to us by a formula that says lowercase q is equal to VQ over I. Now, if I was taking a look at a length of beam and I was to integrate the amount of shear stress that I had over a certain run of this beam, if I did that with respect to length, I would have I would have a force. So the units of Q, lowercase q, would be force per length, and that would be what we would mean by the shear flow. If I was to divide the shear flow by the thickness of the beam, I would end up getting the shear stress. And that would give me tau equals VQ over IT, this formula here. And that is the one that I'm going to require that you be able to apply. So this is the important formula. So we would note a couple of things, that Q is defined as the first moment of the statical area, the first statical moment of the area above or below the point of interest. So I've marked the point of interest with an X, and I would take the area of the top shaded region above the point of interest. I would find the distance from the neutral axis to its centroid. That would give me y bar prime, and I'll denote T or B for top or bottom, and this would be the top area. I could use the bottom part of the area as well, and I would get the same result. Here you can see that the area is larger for the bottom part, but the centroid of the bottom part is closer to the neutral axis than it is for the top part. And Q is just Y bar times the area above or below the point of interest. So you should note that there is a maximum shear flow at the neutral axis because Q is at its maximum at the neutral axis, and Q is equal to VQ over I. Now, we most of the time will typically have a high value of the shear stress at the middle of the beam, and if it's a web that is rectangular, we would typically have the maximum shear stress at the neutral axis as well. But that would be, but the variable t would have something to do with it. So if we had a wide beam near the neutral axis, we might not have the maximum shear stress at the neutral axis, but we would still have maximum shear flow at the neutral axis. So if I'm defining the terms here in the equations that matter, V is the shear in the cross section, Q is the first statical moment of the area above or below, it doesn't matter, you could use either. The point of interest about the centroidal axis, I is the centroidal moment of inertia for the cross section. T is the width of point of interest on the beam. And for the rectangular cross section, tau max is 3V over 2A. We would just know that if we had a rectangle, if we had a circular cross section, tau max is 4V over 3A. So these two formulas can be very useful. They can save you a lot of time and not having to apply this particular formula because it is a bit more involved to calculate Q and I. So no need to do that if you've got a rectangular cross section. And we would note that the distribution of the stress is going to look something like this. It's going to it's going to be 0 at the top because there is no area above the top. So Q is 0 at the top and at the bottom. And we would approach a maximum value, usually somewhere around the neutral axis. So let's do an example. So for the beam below, I'd like to determine the transverse shear stress at the points A, B, and C on the cross section. C is at the neutral axis or at the centroid. B is halfway between the centroid and the top of the beam, and A is the very tip top of the beam. And the maximum shear in the beam is going to occur at the left support. It is 840 newtons. So for point A, Q, capital Q, for point A is 0 because we have no area above point A to take a moment about. So QA is equal to 0. QB is equal to Y bar for B times the area above B. So Y bar would be 22.5 centimeters up to this point here, the centroid of the area above B, times 15 centimeters times 40 centimeters, which is the area above B. And when I do the computations, I come up with 13,500 cubic centimeters. Divide that by 10 to the 6th to get cubic meters, and we would have 0.013500 cubic meters. I could do something very similar for point C, which is at the neutral axis, or the centroid. So Y bar for that would be 15 centimeters. And then I would have 30 by 40 for the area, and that would be centimeters cubed. That's 18,000 centimeters cubed, or 0.01800 meters cubed. Then I calculate that as BH cubed over 12. And then since these are in centimeters, I need to multiply by 10 to the negative 8th to get to meters to the 4th. And the moment of inertia of the section is 0.0072 meters to the 4th. The thickness of the section is 40 centimeters or 0.4 meters. Now all I need to do is apply the formulas tau equals VQ over IT, substituting the corresponding values into the formulas. And I end up with 0 for the transverse shear stress at A. I end up with 3,937 pascals for the shear stress at B. And I end up with 5,250 pascals for the shear stress at C. So as we would expect, the shear stress is greatest at C, which is right at the neutral axis. It is greater at B than it is at A, and it is, in fact, it is 0 at A. And that concludes lesson 14.